Good morning. In the last two lectures, we have been discussing the wave equation and its solution. We started the discussion using an elastic rod as an example. So, we considered a disturbance in the elastic rod, and the disturbance was such that there were displacements introduced, deformations introduced inside the rod, and we looked at the propagation of these disturbances in the same direction as in which the displacements were introduced. So, we had a situation where we had longitudinal waves. There were displacements, and the displacements in the rod propagated in the same direction in which we had the displacements. And starting from this, we derived an equation which governed the evolution of these displacements, and this equation was the wave equation. I then told you that the same equation appears in a large variety of situations where we have the wave phenomena. So, if you consider a stretched string and pluck it and look at the evolution of the disturbance, again it is governed by the same wave equation, the main difference being that we now have a transverse wave. The displacement, the disturbance is perpendicular to the direction in which the wave is moving around. The same wave equation also applies for electromagnetic waves, where we have disturbances in the electric and magnetic field. And in the last class, we discussed how to work out solutions for the wave equation. So, we considered two specific situations. The first one was plane waves, where we had a planar symmetry, and the second situation that we discussed, we had spherical waves where we had a spherically symmetric situation. Now, today let us first start off by discussing a few problems related to solutions of the wave equation. So, the first problem that we are going to discuss is the problem is given over here. So, you have a displacement xi at the time t equal to 0, at the time t equal to 0. So, this is at the time t equal to 0, the displacement xi, the disturbance xi, is given by this function 4 divided by 4 plus x square. And the problem is, the question is that we have to first draw this function. So, draw the disturbance, the form of the disturbance as a function of x at the time t equal to 0. So, let us draw this function. It is very important to be able to draw functions. It is also equally important to be able to guess a functional form for a graph. So, if you see a graph, it is also important to be able to guess the functional form, and this intuition develops after you have drawn a large number of functions. So, let us draw this function. So, let us first ask the question, what is the value of xi at x equal to 0? So, at x equal to 0, xi has a value 1, it is the ratio 4 by 4. So, let me draw this here. So, this is xi and this is x, and at x equal to 0, xi has the value 1. That is the value at x equal to 0. Now, as x increases, just look at this, as x increases, the value of xi goes down from 1, and as x tends to infinity, the value of xi becomes 0, approaches 0 asymptotically. So, this function xi has a maxima at x equal to 0, and then the value falls off at as you go further and further away. So, the graph looks like this. It falls off as 1 by x squared as you go further. So, graph looks something like this. So, this is xi at t equal to 0. That is the first part of the problem. Now, the second part of the problem is that we are given the information that this is a right propagating wave So, as time evolves, this whole, it is a right propagating wave propagating towards the right with the speed Cs, or which I have denoted by c, 2 meters per second. And the problem is that you have to write down the full time dependence of this displacement. So, let me repeat the problem. You have been given the displacement xi at the time t equal to 0. The functional form of xi at t equal to 0 is given, and we are also given the information that this disturbance propagates to the right as a right propagating wave with the speed c 2 meters per second. So, the problem question is that now we have to write down what the functional form for the space time for x and t dependence of this displacement. Now, we know that if you have a right propagating wave, if a function f x is a right propagating wave, then you have to replace x by x minus c t. Any arbitrary any function of x minus c t represents a right propagating wave, and here the function has this form 4 by 1 4 plus x square. So, it is quite straightforward that the right propagating wave, if this function is a right propagates to the right with the speed c, then the wave is given by this expression. This will be 2 t square. So, this is the full time dependence of the displacement if it is a right propagating wave. Right propagating wave means that you have to replace x by x minus c t, and c, the speed of sound, now has a value, the speed of elastic whatever it be, the phase velocity now has a value 2 meters per second. So, once you replace that, you have the right propagating wave. Finally, the third part of the problem is that we have been asked to draw the displacement. This is at t equal to 0, we have been asked to draw the displacement at t equal to 3 seconds. So, what will happen after 3 seconds is that the whole displacement pattern would have shifted to the right by Cs or c, which is c into t, which is in this case it would have shifted by 6 meters, because the speed is, the phase velocity of the wave is 2 meters per second, and you are interested in the wave in the disturbance pattern after 3 seconds. So, the whole thing would have shifted by 6 meters, and this is what the pattern is going to look like. The whole thing would have shifted here by 6 meters. So, the whole thing is shifted. This displacement is 6 meters. The whole pattern has shifted. So, I can draw it for you again over here. It has shifted like this. The whole pattern has shifted by, and it was originally centered here, it has the center has shifted, so has every point, and it has shifted by 6 meters. Okay. So, that is the first problem which I wish to discuss. Now, let me take up the next problem. The next problem is as follows. We have 4 different functions, 4 different functional forms for the displacement xi, and the question is, do these represent travelling waves? Do these functions represent travelling waves? If yes, then what is the speed of the wave? So, how do you decide if a function represents a function of position and time, if it represents, does it represent a travelling wave? In the last class, we have seen that you have 2 kinds of travelling waves. You have a right travelling wave and a left travelling wave. So, if I have some function f of x plus c t, f1 of x plus c t, where f1 could be any arbitrary function, provided it is differentiable and you have it is well behaved, it is a right, it is a solution of the wave equation, and it is a right, it is a left travelling wave, because we have x plus c t. So, the whole pattern moves to the left. This is a left travelling wave and it is a travelling wave solution, And if you have another function, any arbitrary function for that matter, of x minus ct, this represents a right travelling wave. The function should be differentiable and it should be well behaved. That is the only condition. Then it will be a solution of the wave equation and it represents a right travelling wave. So, what we have to see is does this match with any of these two? If it matches with this, it is a left travelling wave. If it matches with this, it is a right travelling wave. So, let us look at the first problem, the first expression that is given A. In this expression, we have the displacement as a function of x and t, and it is sine square pi ax plus bt. Does this match with, the question is, does it match with any of these two forms, any of these two standard forms for the left or the right travelling wave? Now, it should be clear that if A and B are both positive, then this is a left travelling wave, travels along the negative x axis if both A and B are positive. If any one of them is negative and the other is positive, then it is a right travelling wave. Again, if both are negative, it is a left travelling wave. So, this does represent a travelling wave. It is of the form where it is a function of x plus some constant into time. So, if you interpret this as x plus a constant into time, a function of x plus a constant into time, that constant is the speed of the wave. So, for problem A, the speed, see, if you interpret this as x plus a constant into time. So, this, if you interpret this thing as a function of x plus a constant of time, let me do it explicitly for you here. The answer will then be clear. Xi x t is equal to a sine square pi, I take a common outside, a x plus b by a t. So, this is the same function as the one which we have been given, and you see that this is of the form where it is a function of x plus the speed of the wave into t, where you can easily identify what Cs is. Cs is the ratio of the constants b by a. So, this does represent a travelling wave, and the wave speed of the wave is the ratio of b by a. Now, the next question is, does this B, so this is a travelling wave, does B represent a travelling wave? So, if B has to represent a travelling wave, it should be either of this form or of this form. Now, B, the function B, for problem B, the functional form of xi, the displacement, which is now a function of x and t, is given to be sine pi ax square plus bt. Now, notice that ax square plus bt is neither this, it is not x, you cannot write it as x plus a constant into time, neither can you write it as x minus a constant into time. So, it is quite clear that this does not represent a travelling wave. Let us take up part C of the problem. So, in part C, you are given a displacement. Now, the displacement is a function of the position in 3-dimensional space. So, in the earlier two problems, we had a disturbance which was there only along the x axis. In part C, in the part C problem, the displacement xi is a function of all three coordinates. So, we have represented it through a 3-dimensional vector r. So, vector r has all three x, y and z in it, and the functional form of xi is given over here. Xi is the exponential of minus ax plus by minus t the whole square, the square of this whole expression, divided by L square. So, L is some number of the dimension of time, because this whole thing has to be dimensionless. So, the question is this a travelling wave, and if it is a travelling wave, what is the speed? Now, what we had written down here was for a wave in one dimension, for a wave along the x, specifically along the x axis. Now, if I have a plane wave in some arbitrary direction, then I can write it as f, I can write the left propagating wave as n dot r, where n is the unit vector in the direction in which the wave is going. So, this represents a wave propagating along the direction n, and this represents a wave propagating along the direction minus n. As time increases, the wave goes forward along this direction, this wave, and this represents a wave which goes along minus n direction as time increases. So, this is how you would represent a plane wave in any arbitrary direction. Here n is the direction of the plane wave, which in this case is along the x axis. So, n would be just the unit vector along the x axis. Now, can you write this in this way? If you can, then it is a travelling wave, it is a travelling plane wave actually then. So, the question is, can you write this in that form? Just look at it for a few minutes and it will be clear whether this can be done or not. So, look at the argument over here. The argument over here is Ax plus By, and then you have a minus t. So, let us just focus on this Ax plus By. So, we can write this as the square root of a square plus b square into the unit vector n dot r, where n, the unit vector n, is a into the unit vector I along the x axis plus b into the unit vector j along the y axis divided by a square plus b square. So, you can, it is quite straightforward to check that this is a unit vector, because if I take the length of this n dot n, I will get a square plus b square divided by a square plus b square, which is 1. So, this is indeed a unit vector, and n dot r into this number is indeed equal to this. So, we have been able to write this as a number into a unit vector dot r. So, we can write minus Ax plus By minus t as equal to square root of a square plus b square n dot r minus 1 by square root of a square plus b square into t. Right. So, what all that we have done is we have written Ax plus By minus t as a overall factor of square root of a square plus b square into this unit vector n dot r minus this number into t. So, this is exactly the same as this. Now, it should be quite clear that the argument of this function, which is there in the exponent, has now been written in this fashion, right. So, the argument of this function has now been written in this fashion. So, it should be clear that this is indeed of this form, unit vector dot r plus c t. So, what you can say is that this does represent a travelling wave, and if you compare this with the way we have written the argument is over here. So, this is a function of this quantity, and that quantity which it is a function of can be written like this. So, you see that it is a function of n dot r plus this should be, this is minus. So, this is okay. So, we have, so this represents this kind of a wave, this represents this kind of a wave, and by just comparing this expression with this expression, you can identify that the speed of the wave is 1 by a square plus b square. So, let me recapitulate what we have learned. We learned that this does represent a travelling wave. It represents a wave travelling along this unit vector, and the speed of the wave is square root of a square plus b square, where a and b are the two constants which appear over here. Okay. Let me now take up the fourth problem. The fourth problem is again one dimensional. The displacement xi is a function of x alone and only one spatial variable x and time, and the functional form of xi is given over here. If xi is to represent xi, this functional form for xi xt is to represent a travelling wave, it should be either a function of x plus ct or x minus ct. The function that we have over here is sine pi, then we have ax square plus b, this should be t square, sorry, bt square plus 2 square root of ab x t. Question is it of the form where it is a function of x plus ct or x minus ct? Now, you can simplify this to address this question. We simplify this expression a little bit. So, this is the expression that we start with, and we can simplify it a little bit. So, xi x t can be written as sine pi, and notice that this whole thing over here is the whole square of square root of ax plus square root of b t. This expression is exactly the same as what I have written over here, because when I square this I will get the first term, the square of this will give me the second term, and the cross term 2 times this into this is going to give me the third term. So, the same displacement is expressed, the displacement is now expressed like this, and it is very clear that this is of the form where it is a function of x plus ct, where c has the value square root of b by a, right. So, this wave, this is indeed a travelling wave, and it has a speed the square root of b by a. So, this is a travelling wave, and its speed has also been calculated. Let me now take up a different problem, the final problem which we shall be discussing today, and this problem is as follows. So, in this final problem that we are going to discuss, we have a disturbance in a steel rod. The steel rod, the length of the steel rod is aligned with the x axis. So, the displacement, the disturbance varies along the x axis and it evolves with time. And the functional form of the displacement of the disturbance is given over here. Xi represents the disturbance, which is a displacement in the same direction, x along the x direction. Xi as a function of xt is a e to the power minus x minus cst whole square divided by L square. So, e to the power minus x minus cs into t whole square divided by L square. And a, the magnitude of the displacement, is given to be 10 to the power minus 4 meters. L over here, which has dimension length, is given to be 1 meter. So, the first problem, the first question that is asked is as follows: where is the displacement maximum at the time t equal to 10 to the power minus 3? So, the first question that is asked is, at the time t equal to 10 to the power minus 3, where is this displacement maximum? At what value of x is the displacement maximum at the time t equal to 10 to the power minus 3 seconds? Now, let us just look at this function. When does this function have the maximum value? It should be quite clear that this function has the maximum value when this argument x minus cst becomes 0. When this argument x minus cst becomes 0, this xi has the largest value. The largest value is a. If x minus cst is more than 0, the value of xi falls. So, the value of xi is maximum when x equal to minus cs into t. So, the maximum displacement is going to occur at the point x is equal to cs into t. So, this is where the maximum displacement is going to occur. So, for this, to determine this position at t equal to 10 to the power minus 3 seconds at 1 millisecond at the time equal to 1 millisecond, to determine the point where the maximum displacement is going to occur, we need the value of the speed of sound. And we know that the speed of this wave, the phase velocity of this wave, this elastic wave in the solid, is the square root of the Young's modulus divided by the density. And for this particular solid, the steel rod, the Young's modulus has a value 2 into 10 to the power 11 newtons per meter. So, this is 2 into 10 to the power 11 divided by the density of steel is 8000 kgs per meter cube. So, this has to be divided by 8 into 10 to the power 3, and then I have to take the square root of this. So, 2 and 8, what I have left is 1 by 4, the square root of 1 by 4 is half, and 10 to the power 11 divided by 10 to the power 3. So, what we have is 10 to the power 8, and the square root of 10 to the power 8 is 10 to the power 4, which gives us 5000, and we are working in the meters SI units. So, this is 5000 meters per second. This was kg per meter cube, this was newtons per meter. So, finally, the speed of that elastic wave inside the steel rod is 5000 meters per second. Just to remind you, the speed of sound in air is few hundred meters per second, around 300 meters per second. So, the disturbance in the steel, which is equivalent to sound propagating in steel, propagates at a much faster speed. It propagates at the speed 5000 meters per second, right. So, sound propagates, this disturbance, elastic disturbance propagates at a speed which is much faster inside the steel, much faster than sound propagates in air. So, we have determined the speed is 5000 meters per second. We can now determine the value of x where you have the maximum displacement. This is going to be 5000 into 10 to the power minus 3. So, the value of the position where you will have the maximum displacement at 1 millisecond at the time 10 to the power minus 3 seconds is going to be 5 meters. So, at a distance 5 meters away from the origin x equal to 0, you are going to have the maximum displacement at the time t equal to 1 millisecond. The second part of this problem, part B, is as follows. We have to plot the displacement xi at the fixed point 5 meters as a function of time. So, at the fixed point, fixed position x equal to 5 meters, we would like to determine the behavior of the displacement as a function of time. So, the displacement, we are told that the displacement has this functional form. It has an overall coefficient a, amplitude a, and then it is e to the power minus x minus cs t whole square divided by L square. And we have to plot this as a function of time at the position x equal to 5 meters. So, let us ask the question, at what point, at what instant of time is the displacement going to be maximum at x equal to 5 meters. So, that is going to occur whenever x is equal to cs t. We have just determined the value of t, we have just determined this. So, at the point x equal to 5, the displacement is going to be maximum, I will call this t maximum, at 10 to the power minus 3 seconds. The displacement is going to be maximum when this argument is 0, x we are told to look at the point x equal to 5, and we have already found out that the displacement is going to be maximum, this argument is going to become 0 when t is equal to 1 millisecond. So, we already know this. Now, we want to plot this xi as a function of time. So, let me write any arbitrary time instant as the difference from the time instant when the displacement is maximum. So, this t maximum refers to 1 millisecond. This is the instant when this xi is maximum, and if you look at any arbitrary time, the difference from this time instant when the displacement is maximum, I am calling delta t. So, I can now represent the displacement at 5 meters as a function of delta t, the difference in time from when it is maximum. So, if I substitute t by t maximum plus delta t, then xi at the point 5 and as a function of delta t now is equal to a e to the power minus 5 minus cs Tm minus cs delta t square divided by L square, and the maximum time at the time when Tm, when the displacement is maximum, these two exactly cancel out. So, what we see is that a is e to the power minus cs square delta t square divided by L square. So, as you move away from the time when the displacement is maximum, the displacement falls off like a Gaussian, e to the power minus proportional with some constant of proportionality to delta t squared. How does this function look like? So, let me draw it for you. this is the displacement, this is Tm. As we look at a time, another different time instant. So, if you look at a different time instant, say this time instant, this difference is delta t, and when delta t is 0, this has the maximum value a, and as delta t increases, this falls as e to the power minus delta t square with some constant on top over there. So, it falls like this. So, that is the displacement as a function of time at the point x equal to 5. To make sure we have really understood everything, how would the displacement look as a function of time at the point x equal to 6? The point is that you would get exactly the same functional dependence, except for the fact that everything would have shifted by Cs. So, at the point x equal to 6, the maxima is going to occur at a slightly later time, 1 by Cs, and the whole curve would have shifted by the same amount, 1 by Cs, same amount of time. Okay. The next part of this problem is to determine the velocity of this elastic medium as a function of time at the point x equal to 5. So, we have to determine xi, the velocity, sorry, we have to determine the velocity of the elastic medium, velocity of the elastic material as a function of time at the same point x equal to 5. So, let us calculate the velocity. How will you calculate the velocity? This gives the displacement. So, if you differentiate this once with respect to time, let me remind you again what it gives us. This is the elastic rod, and because of the disturbance, this element of the elastic rod will move around. So, because of the disturbance, it may move here or it may move here, and as it moves around, so this is the same rod, and because of the disturbance, this particular element here has now moved over here, and this is the disturbance xi xt. This is the point x. So, the time derivative of this del xi del t tells us the speed with which this point, with the material at this point is moving. This particular bit of the elastic material is moving. So, we have to calculate the time temporal derivative of this function which gives the displacement. So, when you differentiate this, you will pick up so you have to differentiate this exponential. So, you will get this whole thing, that you will get the same exponential back, and then you will multiply it by the derivative of this function. The derivative of this function is going to first have a minus sign, factor of 2, then you have to differentiate this, which gives us another minus sign into Cs. So, the velocity, this is the velocity at any point x, is going to be a 2 because of this, then x minus Cst x minus Cst into this minus sign over here, and then when I differentiate this, I will get another minus sign into Cs, this divided by L squared into xi into e to the power minus x minus Cst So, we have to now plot v as a function of time at the point x is equal to 5. Now, so we have to focus at the point where x is equal to 5. Now, the point to note is this, that when t is equal to Tm, that is the time instant when the displacement is maximum, the velocity is exactly, this argument becomes 0. So, the velocity is 0. When t is less than Tm, the time instant when the displacement is maximum, t is less than Tm. So, this argument is positive, the velocity is positive. When t is more than Tm, the velocity, this is more than this. So, the velocity is negative, right. So, we see that the velocity is positive at all times before the displacement reaches its maxima, and then it becomes negative. So, this is very easy to interpret. This is the, we are looking at this particular element of the elastic medium. It moves, after some time it moves here, and then the motion will, at an even later time it may have moved further away, and then at some instant it will reach the maximum displacement, and then it will move back. So, the velocity is positive until the maximum displacement is reached. At the maximum displacement, the velocity is 0, that is how the maxima is defined, and then the velocity becomes negative. So, this is what you also see here. If you plot this curve, I will request you to sit down and put in the values and actually plot it. Right now, I will just plot it schematically, and it looks like this. This goes to 0 as at large time, and this instant of time where the velocity is 0 is the Tm, the instant when the displacement is maximum. Okay. So, that brings us to the end of the problems which I wanted to discuss. So, for the rest of today's class, we shall be discussing, we shall discuss standing waves. So, the next topic that we are going to take up is standing wave. It is a continuation of solutions of the wave equation. So, we are going to discuss the topic that we are going to discuss is standing waves. So, let me get rid of this and so, the situation that we are going to consider is as follows. We have we will discuss it standing waves in the context of a stretched string. So, we have a stretched string which I show over here, and the string is attached at two endpoints. So, this is one endpoint and this is the other endpoint. The string is attached at these two endpoints, it is held tight by the two endpoints. The two endpoints cannot vibrate, and we shall be considering the transverse disturbances of the string. So, the string can be disturbed like this in the transverse direction. This displacement in the transverse direction could vary with x, this is x, and it could also vary with time. So, we are interested in the vibrations of this string. The string has a length L, and this point corresponds to x equal to 0, this point corresponds to x equal to L. So, we are interested in studying the solutions of the wave equation. So, these displacements are governed by the same wave equation which we have been studying all along. The equation is the same, the sound speed, the speed, sorry, not the sound speed, now the speed of these transverse vibrations in this stretched string are different. It depends on the tension and mass per unit length of this string, but the equation governing it is the same, only that the speed of sound, the phase velocity is different. So, we want to look for solutions to this equation. So, the transverse displacement disturbances in this string satisfy this equation. Xi represents the transverse disturbance. C here is the speed for this wave, which depends on the tension of the string and the mass per unit length of the string. The value of C depends on that, and these displacements are governed by this equation. We now have one additional thing that we have to take into account. It is the boundary condition. Until now we have not discussed the boundary conditions at all. So, in our discussion of waves till now, nowhere have we discussed what the boundary conditions are. It could be, the wave could be any arbitrary function. We have not discussed any boundaries. Here in this particular problem we have to impose the boundary conditions. So, the boundary conditions here are the fact that xi is 0 at the two endpoints. So, at all time instants xi is 0 at this point where the string is attached. This point does not get disturbed. Similarly, the other end of the string, the other extremity of the string, xi as a function of L at the other endpoint L as a function of time is also 0. So, at the two endpoints the string is fixed. The string is fixed here and here. These 2 points are not disturbed, the rest of the string can be disturbed. So, we want to find solutions of the wave equation which have this boundary, this boundary condition, and we could take whatever that we have discussed till now, the plane wave solution that we have discussed until now, and apply these boundary conditions, but we shall proceed to solve this equation in a different way, so that it gives you exposure to another method of solving the wave equation. So, we are going to use the method of separation of variables. So, we are going to look for solutions xi x t, we are going to look for solutions to the wave equation xi. So, we are going to look for solutions which are a product of two functions, one of x, I am calling this capital X, and another of time alone. Okay. So, we are expressing xi, the disturbance, as a function, as a product of two functions. The first one, capital X, is a function of the position alone. The second function, capital T, is a function of time alone. So, we are expressing the disturbance in this string as a product of two functions, one of position alone and one of time alone. So, we are taking a trial solution that looks like this. So, if you take such a trial solution and put it in the wave equation, what do you get? So, let us look at this term by term. The first term over here is the spatial derivative of xi. So, when you differentiate xi with respect to x, if xi has this form, you now have only derivatives of this function. Derivative with respect to x does not affect this function at all, and for this function the derivative with respect to x is an ordinary derivative. There is no need to talk about a partial derivative anymore, because it is the derivative of a function of only one variable. So, the term the first term over here becomes t into the derivative, ordinary derivative with respect to x of this function x, which is a function of x alone. And similarly, the second term in the wave equation, which has a partial derivative with respect to time, when I take a partial derivative with respect to time, I have to keep x fixed. Now, when I take a partial derivative with respect to time here, it does not affect this function because it has no time. So, it is only on this function that the derivative acts, and you can replace it with the total ordinary derivative because there is no variable other than t in this function. So, the differential equation now becomes this. So, the partial differential equation that we had started out with, if you write the take a trial solution which you write as a product of a function of x and a function of t, the equation now becomes this. And we can divide this equation throughout by x t. So, I am going to divide it by xi, which is x into t. I am going to also divide this by xi, which is x t. So, I have divided this whole equation by xi, which is t into x, and if I divide this by xi, then we see that the term t cancels out from this. So, this the time dependence cancels out from this, and the term x over here cancels out from this. So, the equation that we are left with, let me write it down over here. So, this what we have is only these two terms over here on the left hand side. So, the equation that we are left with is 1 by x d square x dx square is equal to 1 by c square 1 by t d square t d t square. So, the ordinary differential, the partial differential equation that we had now gets simplified considerably, and we have an equation in terms of ordinary derivatives only. On the left hand side, we have the partial differential equation essentially now gets converted into this, under the assumption that the solution is a product of two different functions, one of x alone and one of t alone. The partial differential equation gets simplified to this. The term on the left is a function of x alone, and the term on the right is a function of t alone. Now, here we have a function of x and here we have a function of time. I can vary x arbitrarily, I can vary time arbitrarily, but still this equality holds. What this tells us is that this has to be equal to each function has to individually be equal to a constant. So, we will call this constant alpha. So, what this tells us is that this function of x, this function of time, if they have to be equal, they have to be separately equal to a constant, individually equal to a constant, and that constant we are going to call alpha. So, let me stop here for today's lecture, and we will resume our discussion here tomorrow. So, we are going to work out the solutions of this. We will get two different separate differential equations, they are ordinary differential equations. So, let us work out the solutions to these ordinary differential equations in the next class and then impose the boundary conditions.